Hey there, chemistry students. This is Miss Reork. This is Vodcast 6.1, where we're going to start talking about how to take all of that stuff that we've been learning so far and stick it all together. All right. So what is the meaning behind a chemical reaction? Well, we know the law of conservation of matter says that no matter or no mass can be created or destroyed. It simply just changes form. And we've seen that with our chemical reactions. Well, on this balanced chemical equation, it tells us just more than that. It tells us that, hey guys, guess what? For every 4 ammonias that we have reacting, and for every 5 oxygens that we have reacting, we can make 6 waters, and we can make 4 nitrogen monoxides. Okay, so that's what it says. But a chemist actually likes to say in quantities, because remember, we use moles as a counting unit. So we say 4 moles of ammonia reacts with 5 moles of oxygen, and those would come together to form 6 moles of water and 4 moles of nitrogen monoxide. Okay, so stoichiometry, which we're getting ready to do, just refers to the relative quantities of moles. Okay, and so we use this thing called a mole ratio to compare moles of one thing to moles of another. So if I was to ask you the mole ratio of ammonia, which would be NH3, to oxygen, you would say the mole ratio is a 4:5 ratio. Okay, it's very important that you understand that because we're going to be using that in our calculations. So where did I get these numbers? From the balance coefficients, or from the coefficients of our balanced chemical equation. All right, so how do we place this into practice? Well, let's look at this. It says that balanced equations are like recipes. Predict how many cheese sandwiches, as defined by the picture above, you can make if you have 6 pieces of bread. It's supposed to say bread, not break. 6 pieces of bread and 4 slices of cheese. Well, if we were to do it by the cheese, we could make 4 sandwiches, but they wouldn't be complete sandwiches. We could only make 3 complete sandwiches because we would have 2 pieces of bread and 1 slice of cheese, and then we would have 3 slices of cheese left over. All right, well, what if I needed to make 14 sandwiches? How many slices of bread would I need? Well, for 1 sandwich, we need 2 pieces of bread. Right? If we need 7 sandwiches, we would need, let me change that. If we need 14 sandwiches, we would need to have 28 pieces or slices of bread. Okay? And that's stoichiometry. All right, so Chemistry Cafe cook has a loaf of bread which contains 33 slices and a package of cheese which contains 15 slices. He's making sandwiches that have 2 pieces of bread and 2 pieces of cheese. How many sandwiches can he make? Well, according to the 33 slices, if we divide that by 2, we could make about 16 sandwiches, right? 16 full sandwiches. And if we have 15 slices of cheese and we need to put 2 on each one, we could make about 7 sandwiches. So how many can we make? 7. We don't count the half. We're talking about full sandwiches. Okay, here's another example. A tricycle factory gets a shipment with 400 seats and 600 wheels. Okay, so 400 seats and 600 wheels. How many tricycles can we make from 400 seats and 600 wheels? Now, here's a picture of a tricycle, and we're going to imagine that all of the wheels are the same size. I know it doesn't make sense, but we're going to imagine that. Okay, so we need 3 wheels per tricycle, and we need 1 seat per tricycle. Okay, so if I had 1 seat, I could make 400 tricycles. With 3 wheels per tricycle, I can only make 200 complete tricycles. So how many will I make? 200, right? This makes sense. All right, so let's apply this to chemistry then. The only thing that we're going to add here is that mole ratio. Everything else is the same. You know how to do all of this already. All right, so it says how many moles, balanced chemical equation already, how many moles of water are going to be produced if 0.176 moles of O2 are used. Okay, so we're going to start with the number that they give us in the problem, and we're going to multiply by a fraction. Now, this is where we can go from moles of one thing to moles of another, but we have to have our mole ratio. So we want to get rid of moles of oxygen, and I want to find out moles of water. Okay, well, this is our mole ratio here. What's my ratio of water to oxygen? Let's say 6 to 5. So we put the 6 here because it's the coefficient for water, and we put the 5 here because it's the coefficient for the oxygen. Moles of oxygen cancel. We're left with moles of water as our units. And now all we have to do is the math. So 0.176 times 6 divided by 5 gives us 0.2112. And we need 3 significant figures. So the final answer would be 0.211 moles of water. You're like, oh my gosh, this is so easy. You're right, it is. Let's do another one. Okay, example 2, same balanced chemical equation. How many moles of nitrogen monoxide are produced in this reaction if 17 moles of water are also produced? So look, we're going from product to product, and that's something we can do because we're comparing them using moles. Okay, so 17 moles of water. We've got to get from moles of water to moles of nitrogen monoxide. We want moles of water to cancel. So remember, whatever unit goes here, we pull it straight down to cancel it. We want to find moles of nitrogen monoxide. Can I do a direct conversion from one to the other? Yes, I use my mole ratio. So nitrogen monoxide has a 4 in front of it, and water has a 6 in front of it. Okay, there's my mole ratio. Moles of water cancel. I'm left with moles of nitrogen monoxide in my answer. And now all I have to do is the math. So we plug in 17 times 4 divided by 6, and that gives us 11.333 repeating. Okay, 2 significant figures, so we'll have 11 moles of nitrogen monoxide. All right, you should be feeling pretty confident by now, so let's try another one. Example 3, how many grams of water? Oh my gosh, Mr. Rick, you added something new in there. No, I didn't. You know how to do that already. Okay, are produced if 1.9 moles of NH3 are combined with excess oxygen. Okay, here's a word that you guys are going to start seeing. You're like, oh my gosh, what does that mean? What does it mean if something is in excess? It means there's too much of it, right? So you just have more oxygen than you need. That's all it means. So when you see that, that tells you that you don't really have to worry about oxygen. You can just push it to the back. Okay, so we're going to start with 1.9 moles of ammonia because that's what we have in our problem. All right, in order to change from one compound to another, we have to use our mole ratio, and it has to be moles to moles. So we put moles of ammonia on the bottom because that's what we want to go away. And we need to go from ammonia to water. So we're going to go from moles of ammonia to moles of water. Okay, here's where our coefficients come in. NH3 has a 4 and H2O has a 6. Okay, moles of ammonia cancel. We now have moles of water, but we don't want moles of water. We want grams of water, and this part you already know how to do. So what do? We take moles on bottom. We put grams on top. Mole always has a 1 in front of it. And grams here, this is your formula mass, 18.02. Okay, moles cancel. We're left with grams in our answer. That's what we want. So we plug it into the calculator. 1.9 times 6 divided by 4 times 18.02. And the calculator gives you something like 51.357. We have 2 significant figures, so we want to make sure we have 2 significant figures in our answer. The 3 does not make the 1 change, so it's going to be 51 grams of water. So we can make 51 grams of water if we use 1.9 moles of ammonia. All right, example 4. How many grams of oxygen are required to produce 0.3 moles of H2O? Same type of problem. We start with 0.3 moles of H2O. Now, if you're struggling and you're like, oh my gosh, I can't keep up with this, that's okay. You just keep going with me. And when you come to class, I'm going to show you a little roadmap that might help you remember where you got to go. You just got to make sure you remember the roadmap. All right, so we want to get rid of moles of H2O, so that goes on the bottom. And we want to go from H2O to O2, so we're going to go to moles of O2. Numbers here, your coefficients. There's a 5 in front of the O2 and a 6 in front of the H2O. Moles of H2O cancel, but we're not done. We want grams, so we keep going. We put moles of O2 on bottom, grams of O2 on top. 1 mole is equal to 32.00 grams. And now you do your math. And the answer will give you 8. That's actually what the calculator gives you, grams of O2. And that's what we need because we only need one significant figure. All right, here's the last one. We've got 12 grams of oxygen. We are looking from 12 grams of oxygen, how many grams of NO? Okay, so I'm going to show you a ghost. Actually, I'm not going to do that. I want you guys to try this one on your own. I want you to bring it to class, and we'll check your answer in class. You know how to do this because I've just given you 4 great examples, and you know how to go grams to moles, and you know how to go moles to grams. So the only thing that's new here is moles to moles, and I've just shown you how to do that, and that's the easiest part to it. So I'll see you in class.